Hey, I heard that in a movie. No, I did.
That's all I can remember. Oh,
Before you know it, the test is going to be upon us, you know.
40年以后世界要美。
Okay,
Does
so
this school have sinus pills?
That makes sense, right?
no, I don't think so. You
40
can
years
get like
before I finish.
Tylenol at the infirmary.
Where's Jennifer?
Okay, so besides 13 and 15, is that it?
Wait, can you explain like when they say like you have a unit circle or you have like a semicircle,
Oh,
how do
yes.
you do the R for that?
Is this April 1st?
Yes.
Okay, which one is the semicircle? Oh, number 3, the unit circle.
Number 3 and number 11. But it's like just that part.
Okay, number 3, the unit circle traversed clockwise. Oh, a little bit tricky there. Okay, well, we already know the unit circle can be formed from these parametric equations, right? X equal cosine t, y equals sine t, right? But, see, but the problem is they want it to go clockwise. Like, if you use these equations, the particle starts here, like if you plug in 0, and if you plug in pi over 2, it's going to be there, so the particle goes counterclockwise. But they want it to go.
Sorry.
But they want it to go clockwise.
Is it just negative?
So what could I do? How can I change these equations to make the particle go clockwise instead?
Negative sign.
Yeah, you probably got to put a negative on one of these, right? So what?
Negative sign.
Which one? On the sign?
Does it matter?
Well, let's see. If I put a negative on the sign, let's see. If the particle is at t equals 0, it's here, and then t equal pi over 2, it's there. Yep, that'll do it. So there you go. That would be one way. Yep, that'll do it. Where did I just see that? On Stand and Deliver. Yep, that'll do it. And then what, you said there was a semicircle or something?
It was like a curve and
Oh, right there, it says the upper part of the unit circle.
Yeah.
It says the closed curve, which begins at negative 1, 0, proceeds along the x-axis to 1, 0 by the upper part of the semicircle. Oh, so in number 11, see, that's why parametric equations in PCH are so important, yeah? So the particle starts here at 1, 0. Wait, number 11. No, it begins at negative, it starts here. Then it goes along proceeds along the x-axis to here, so straight line. And then it goes to the upper part of the circle. So we're gonna have to do 2 integrals, yeah? So the first one that goes from here to here, you can do that one?
Yeah.
Okay, but what about the one that goes from here to here? So again, x, oh, that's just the normal ones, right? X equal cosine t, y equals sine t, that'll do it, right? Except, oh, I mean, you can make up your own time interval, so we could just leave it like that. Yeah.
What is the
R vector for number 3.
Right here. The position vector.
Oh.
This is it. Remember? This is the same thing as writing it like this. Cosine t,
Oh, yeah.
negative sine t. It's the same thing.
wait, is that because it would be like x squared plus y squared equals cosine t?
Equals 1 then, yeah.
Yeah.
Yep, exactly. And maybe this is a good time to bring it up. What do you guys remember the ellipse one? Oh, it's coming up on number 15, yeah. Okay, let's do number 13 then. Number 13 just looks like computation though, because it doesn't. Okay, let's just do it.
Oh yeah, it just didn't come out.
Okay, so we need R of, no, what am I doing? F of R of t dot R prime t, correct? And we're going to integrate it from 0 to 1. So what is F first of all? The force function is yz x squared xz. R of t is the position vector t squared t cubed. Why am I putting a parentheses there? So what is f of r of t? So what happens when you plug these into there? So this one is y times z, so here's y and z right there, so t to the fifth. This one is x squared, so that one squared is t squared. And then x times z is this times this, t to the fourth.
Never mind.
You got the mistake already?
Yeah, I thought it was t to the fourth.
Okay. Well, what the heck, we might as well finish it for funsies. And then you have to dot that with r prime of t. So that would be the velocity vector. So if this is the position vector, the velocity vector is 1, 2t, 3t squared. And then you dot product them, so you would get t to the fifth plus 2t cubed plus 3t to the sixth. And we can't combine any like terms, so that's it. So we're going to integrate that from, in this case, what was it? What does it say? 0 to 1? Yep, 0 to 1. Okay, that integral is easy. I'm not going to do that one. Okay, now I got to scroll to get to number 15. I thought this was the most interesting of the three problems. I mean, whatever problems there were. An object orbits an ellipse in standard position subject to a force that's your force. I'm gonna have to erase here. So here's your force, vector negative 1/2 y, comma, positive 1/2 x. I'll just write it like that. Okay. Find the relationship between the work done and the area of the ellipse. Okay, so what is the position vector for an ellipse? Impress me. Park. What is the parametric equations for the ellipse? Wayne, you're next. Queen, you're after that.
Isn't it like,
If you're in this class, I'm going to ask you questions.
is it like a cosine?
There you go. A cosine t, b sine t. That is correct. Do you see why that's the ellipse in standard position? I don't believe you guys.
Yeah.
Because
Look.
it's like a circle A.
X equals a cosine t. Look, y equals b sine t. Square the first equation. X squared equals a squared cosine squared t. You know what we should have done? We should have divided by a first. X over a equals cosine t. Y over b equals sine t. Square the equations. And add them and you get x squared over a squared plus y squared over b squared equals 1. There you go, ellipse in standard position. Okay, so once you write these down, isn't it kind of self-explanatory after this? It's just computation, but the surprise is to come at the end. So what is f of r of t? So you have to plug this thing in for y there. So f of r of t equals, so plugging in that there, you get negative 1/2. Why don't we just go negative b over 2 sine t, comma, and then you gotta plug that in for x. So you get a over 2 cosine t, and you gotta dot that with r prime of t, which is the velocity vector. So if this is position vector, you got negative a sine t, b cosine t. Are you guys following? Are you following, Joe?
Yes.
Or are you just cutting up paper?
No, I'm following. I'm like listening. Oh, yeah.
It's a good thing you can multitask. And then if you dot product them, you get a b over 2 sine squared t plus a b over 2 cosine squared t, and we're going to integrate that dt from, what should my limits of integration be if we're going to go around the entire ellipse?
0 to 2 pi.
Okay, 0 to 2 pi. But this one looks good because what happens when you factor out the ab over 2? Factor out the ab over 2.
1.
You get sine squared t plus cosine squared t, which is 1 dt, and you're going to integrate that from 0 to 2 pi, but that's just a constant, so isn't the answer just ab over 2 times 2 pi? which is pi AB.
Where's surprise?
Yes, and then it says, find the relationship between the work done and the area of the ellipse. So what is the relationship? Win? This is the answer. Okay, you don't have to know that part, but what is the relationship between this answer and the area of the ellipse? That one you know. Weren't you in my PCH class?
Yeah, but
Okay.
I heard everything.
I'm gonna purge your letter of recommendation.
Oh, isn't it already something?
That is the area of the ellipse.
That was my guess, just because of the circle.
Think about it. An ellipse is like, look, what's the area of a circle of radius r? What's the area of a circle of radius r?
Pi r squared.
Pi r squared. That's when these two are equal. So doesn't it make sense? The area of an ellipse is pi AB? Because it's like, this is A and B, pi AB.
Oh.
But what if these two are the same, then you get pi r squared.
Oh.
So it's only,
Ta-da!
it says only that equal when the force function is negative 1/2 y.
Yeah, it's only when it's that force function, yeah.
Oh.
I don't know, I guess the book thought it was neat. I thought it was neat. Like, hey, use some body. That's the area of an ellipse. Okay. Okay, now the next thing, so tonight's homework is pretty much the same thing, except there's a theorem we can use to shorten our work, which is called the fundamental theorem for line integrals. Now they go through a long thing about the physics, like what kinetic energy is, and something about the work. Did anybody even read the book, Joe?
Somewhat.
Because like I told you, I'm not really good at physics, but they mentioned something about the work done is equal to the change in kinetic energy.
Yeah.
Is that true? You're in physics C.
No, I took physics 2 last year.
So work done is equal to the change in kinetic energy.
Somewhat.
I have no idea about that.
Wasn't that physics 1 though?
Yeah. I'm pretty sure it was.
But I'm just going to show you how to do the problems. So here, for those of you following on the video, we need to look at some things here. Turn to page 829. So on the bottom, look at it, 829. So look, it says here, work done is equal to the Joe. Work done is equal to the change in kinetic energy. In general, if an object moves from one point to another, the work done depends on the path of the motion, right? Because that's what we did in last night's homework. However, there is an important exception. If the force field is a gradient field, in other words, it is a gradient, then the work done depends only on the endpoints of the path and not on the path itself. But only if the force field is a gradient field.
Force field.
Which of course leads to this. This is on page 830. If a force field is a gradient field, then the work done along any closed path is 0. Doesn't that just make sense? Because if it's a closed path, you're gonna start and end at the same point. So therefore the work done has to be 0. All right, so we're gonna do some examples here. Okay, I'm not gonna do the first example, let's do the second example. So we are on page 830 it says problem. Okay, so for those of you following on the video, find the work done on an object that traverses the circular arc, so again, that's the unit circle again, from 0 to pi over 2, so that's just 1/4 of the circle, subject to this force. So you guys on the video, I'm not even sure you're looking at the book, so I'll write it on the board here. So we have the unit circle. This is r equal cosine t sine t, like this. But only from 0 to pi over 2. So from here to there only. Okay? And then here is your force vector, which is y squared 2xy minus e to the y. So, the fundamental theorem for line integrals. If this is a gradient, then we don't have to do the thing that we did last night. We just have to evaluate it at the endpoints. Because the work done, because apparently if this is a gradient, then that function there, remember I gave you a problem on a test? I said this is a gradient for what function? I think it was not this past test, but the test before. You guys remember that?
Wait, what is the gradient?
That's a vector formed like the partial with respect to x and the partial with
Oh,
respect
yeah.
to y, remember that?
Yeah.
Oh boy! So is this a gradient of something? I mean,
Yes.
no.
No.
This is a gradient of what function, in other words?
A
So the
function.
anti.
XY squared.
The anti-gradient. So what,
Oh, okay.
you guys did this on the test,
Oh,
I
I
remember
remember.
everybody got
It was number 2.
Okay, so what function do you take the gradient of to get this?
XY squared, comma,
X, y squared,
XY,
comma.
XY.
Oh no, you know what we're gonna do? Why am I writing it like that? We're
Yeah.
gonna write it like this. Equals
XY squared
x, y squared
plus XY squared.
Wait, isn't it minus or
Plus
minus e to the y.
comma xy squared? Yeah, it should be squared.
So then just that,
Yeah.
plus c.
Yeah, of course.
Everybody agree, if I take the partials with respect to this, I mean, compute the gradient, you get this. Let's check. Take it with respect to x, then with respect to y, yeah, it is. So this is a gradient, so to compute the work done, we don't have to worry about the curve, it doesn't matter. All that matters is the endpoint. So what is the initial point here?
0.
1, comma 0. What is the final point there?
0, 1.
0, comma 1. So we just have to evaluate this at the endpoints. So what is f of 1, 0? If I plug in 1 for x and 0 for y, what do you get? Oh my goodness.
Cosine.
-1. No.
Negative 1 plus c, and then what is f of 0, 1? Plug in 0 for x and 1 for y.
E, negative E.
Negative e plus c. So if I subtract the two, wait a minute, which one do I subtract from? The final position, yeah? Final position minus initial position. Almost subtracted the wrong way. So of course the c's are gonna cancel out, so you're gonna get negative e minus negative 1. 1 minus e is your answer. That is the work done. So that kind of reduces our work if this is a gradient of something. But that's only if it's a gradient of something. Are we okay with that? Because the next problem is a little tricky. Let's make sure we got the right answer. 1 minus e. Yup, there you go. Okay, here's the tricky one. This is the third example. Compute the line integral where c is the unit circle again. Here. So we got the same unit circle. Cosine t, sine t. And it says t goes from 0 to 2 pi. So that's all the way around the circle. And here is your force vector here, which is y squared plus y, comma 2xy minus e to the y. Now here's the tricky part. This is not a gradient of something, but part of it is.
Wait, why?
Okay, tell me. This is a gradient of what function? What's the function then? What function do I take the gradient of to get this? Huh?
XY squared
Wait, is it?
plus
Yeah, it's not. That's why, but they said part of it is. In other words, if you took this away, okay, let's just take that away. Now, is that a gradient?
It's
Yes.
Of what? What function is it a gradient of?
No.
Tell me,
X squared minus
Oh, yeah.
X Y
It's the
squared
same thing
minus.
as last one.
is it the last one?
Yeah.
Xy squared minus e to the y plus c. Yeah, do I need to put the plus c if we know they're gonna cancel out? Okay, no.
Wait, if it's f of x, y, z, is there a zero term for k or no?
Okay, so does everybody agree? If I took this away, whatever remains is a gradient. It's kind of tricky to see that though. And since we're going completely around the unit circle, what is the work going to be done just for this part over the unit circle, since it starts and ends at the same place? Like it starts here and it ends there.
0.
Yeah, it's going to be 0. So the work done for that part is 0. So that means all we have to do now is, that's the remaining part then. Now we can compute the work done just for this. You guys understand? Because if you take this away, that's a gradient, but we added that in. So for that part, for this part there, the work done is 0, right? Because the starting point and the ending point is the same. Okay, you guys don't believe me?
Wait, but why is the starting point and the ending point?
Because now, this is the original problem. Now you gotta put that in. This part does not contribute to this part, so you gotta do this part by itself.
Yeah, but wouldn't that end up like start from the same position and same position too? F equals y comma 0.
Yeah, but this is not a gradient, so you can't say that's 0. That's only 0 if it's a gradient, the starting and end point. All right, so now, so this part here, then we have to do it like last night's homework. So here is f. What is r, the r vector, position vector? Cosine t, sine t. Okay, so what is f of r of t? F of r of t. There must be a shorter way of writing that.
Sine.
So it's just y, so it's sine t, and then 0. And then, what is r prime of t, the velocity vector? So if this is r prime is gonna be negative sine cosine. Take the dot product of it, so this times this is negative sine squared t, and of course that times that is 0. We're gonna integrate that with respect to time from 0 to 2 pi. Okay, and then you guys remember how to compute this integral? What's the only way, let's put the negative on the outside. What's the only way we can integrate sine squared?
Half.
By replacing it with the identity 1/2 times 1 plus cosine 2t. Oh, minus, sorry. Okay, anti-derivativize that, and you got t minus 1/2 sine 2t from 0 to 2 pi. Plug in the top number. Oi! 2 pi minus 0, and then 0 minus 0 when you plug in the bottom number, and so you just get negative pi. That's the work done.
Okay, wasn't it 1/2? Oh, no, right.
Yeah, I think.
Right.
Well, let's check the answers. Yep, we did it right. Yeah.
You know how the force function is an xyz function?
Uh-huh.
Why do you not need like a k term for the vector?
Because that one is only two-dimensional, that's why.
Why do they have a z then?
I guess this z is 0 then.
Okay.
Z is 0. So, yeah, so tonight's homework is kind of the same as last night, but my guess is most of them are gonna be gradients, except maybe 1 or 2, then you're gonna have to use this trick here. So you're gonna kind of be clever for that. Not that bad, huh? All right, I wanna just see what we're learning next time. Next time we got, oh, Green's theorem. Joe, did you know about Green's theorem?
I heard of it.
That's one of the most powerful theorems in multivariable calculus.